So this talk is called What Mathematicians Can Teach Us About Solving Hard Problems. So it won't be nearly as polished as the first presentation or as funny as the second one, but my hope is there will be a useful practical takeaway from this. So I want to start off by giving you a math problem, and I want you to take a moment to think about how you might solve this problem. What if I asked you, what is the sum of numbers from 1 to 100? 1 plus 2 plus 3 plus 4 all the way up to 100. Take a moment and think about how you might solve it. I suspect some people might figure out, oh, I could go to Microsoft Excel, type 1, 2, 3, click and drag the rows, and I go up to 100 and it'll just sum it for me. That's a cool way to do it. Most of us are programmers, so you might write a for loop and just do it that way and write 3 or 4 lines of code. Notice how that style of thinking changes. Did you figure it out already? What's the no? Don't give the answer yet. Notice what changes when I slightly change the problem to asking what's the sum of numbers from 1 to 1 trillion? What changes about this? More importantly, why does this suddenly become hard? Well, it becomes hard because Microsoft Excel, if you chose to use that option, that'll crash well before you get to 1 trillion rows. Mark, you can try that out and let me know how that goes. He's not going to try. Or even if you were a programmer, you decided to write this with a for loop, you'll start running into problems like this will take some number of hours or days to complete because it's such a large number, or you'll have to deal with integer overflows. This becomes hard because we are using technology to try and solve this particular problem. Now, as it turns out, mathematicians have been solving really hard problems for millennia without the aid of digital technology, for a very long time. And their general approach is this. They go say, okay, this problem is hard. Can I go and turn the problem on its side and reframe it more simply and say, is there a simpler way to look at this problem? And as it turns out, for this one, there is. If we take the 1 to 100 case, if we lay these out on a number line, 1, 2, 3, all the way up to 100, we notice different properties about this problem. So first off, we're going to add up a bunch of numbers and notice that when you're adding numbers, it doesn't matter what order that you add them together. And there's a particular order that simplifies this problem. Let's take the first and last number. So we take 1 and 100, we add them together, and we get 101. Cool, that's a good start. Let's find some more numbers to add. How about we just move in a little bit and take 2 and 99. 2 and 99 added together is 101. So it's 398, 497, all the way down through all the pairs of numbers down to 50 plus 51. Because every time we move to a new pair, we add and subtract 1, and the sum stays the same. So now we have changed the question. The question is now, how many pairs of numbers are there between 1 and 100? Take that and multiply it by the first and last number added together, and we get 50 pairs times 101 is 5,050. And that's the sum of numbers from 1 to 100. Now what makes this an elegant solution is because we're not using technology to solve this problem, this scales really well. What's the sum of numbers from 1 to 1 trillion? It's the exact same question. You take 500 billion pairs, multiply it by 1 trillion and 1, and you get 500 sextillion 500 billion. And that's the answer to that problem. So I think that's pretty neat. And so the takeaway on that particular analogy is when you're presented with a hard problem, pause and take a step back. Resist the urge to reach for a technology to try and or throw technology at the problem, and instead try and rephrase the problem more simply. Look for a simpler way to rephrase the problem. So I wanted to relate this to more of the kinds of hard problems we're solving here at Avature. So I'm going to go over an example that Art and I were working on last year. So we were dealing with a problem where we had to basically 3D scan something, and this 3D scanner would scan, for example, a cup-shaped object. I know that's kind of hard to see on the TV here, but it's just a cup with a bunch that's represented by a bunch of points. And there are a lot of hard problems to solve. One of the hard problems we'll solve was, if you give me this point cloud, a bunch of 3D points, can I find some surface area calculation based on that? Well, if you just have points, you can't find a surface area, but the way to solve this is to create a polygon that makes out the surface of those points, and then you can do a surface area on that. And so we basically need to do something called triangulating a polygon. The algorithm that we chose was it's called the Delaunay triangulation. I won't go super into the details, but basically you see on the right there in this animation, a Delaunay triangulation will, for given 4 co-located points, depending on where those points are, it'll try to find the orientation of 2 triangles based on how uniform that triangle is. So if you get a really kind of skinny stretched triangle, it'll flip the other way and try to orient those triangles a different way. The fact that this example has math is actually irrelevant. Think of it like this. We had a hard problem on a project. We were going to solve it by using some algorithm. But, and I forgot to point out on the previous slide, on that left graphic, in order to get that kind of property, you have to do a lot of complex calculation, and it's computationally expensive. But the goal was to minimize the errors so that we could accurately calculate the surface area of this object. So what this got us was really accurate scans. The Delaunay transformation or triangulation did actually do a good job of triangulating a polygon from which we could calculate the surface area, but it got us 60 plus seconds per scan. Sometimes more, sometimes like 2 minutes or 3 minutes. And that's a really long time. It doesn't matter if we're talking about an assembly line or a self-driving car, 60 plus seconds is just not an acceptable time per scan. So what are some ways that we can solve this? Well, what we could have done is basically throw technology at the problem and said we could scale horizontally or we could scale vertically. But we're trying to, the lesson here is to resist that temptation and instead go back to the drawing board. And I think this was actually Art who first brought this up when we had this problem. And we said, look, let's go back to the drawing board and figure out, are we making this too hard? Is there a simpler way to triangulate a polygon while keeping the accuracy high? So it's just like that 1 to 100 problem. We actually went out, we said, okay, here's what we get. We have this laser that we're scanning this object with, and we get a row of points. And then some number of microseconds later, we get another row of points. And as you keep scanning, you get another row of points. And it turns out the number of microseconds between each scan is not predictable, but you will ultimately end up with a point cloud, a 3D point cloud. And we thought, well, let's just do this with the simple case. Let's take the first couple rows and just draw a line right through them and just kind of naively connect the dots here and makes a bunch of triangles. And then when we get another row, draw a line through it and again, naively create some triangles. And you go all the way through here and we've triangulated a polygon in a kind of unintelligent way. So what this did for us was the computation for this was insanely fast, like several orders of magnitude faster than the previous algorithm. However, you see here, you still get some long, skinny triangles, and if there's significant 3D curvature between there, then we're going to get some errors. However, it was so fast that we were able to do something else. The scanner had a dial on it, basically, where you could turn it up so that instead of scanning maybe 2,000 points that are spaced apart, you could turn it way up to get like 20 or 30,000 points that are spaced apart. And we started getting scans more like this, and we were able to turn the dial way up because it was so fast. And now we got points that are closely packed together. And with the naive triangulation algorithm, even if you get skinny triangles in here, the points are so close together that it doesn't matter. The errors diminish to zero as those points get closer together. So to show a demo of what we did, I test this out. This is going to be a real-time video, and I have a piece of styrofoam that I'm going to scan, and we're going to see what happens in real time. So I'm holding onto it with my hands. I scan the styrofoam. You saw it go through the laser right there. And then 4 or 5 seconds pass, and as soon as a web browser pops up, it's done. The web browser pops up for us to just kind of confirm that it actually scanned correctly. And you can see when I rotate it here, you'll see my hand holding this basically piece of trash. So that went pretty quickly, and I'll show it again. And again, I'll describe, scan the object, half a second passes, then it started the calculation, 4 or 5 seconds pass, and it's basically done. And what we end up doing is we took something that took 1 to 2 minutes and got it down to 4 or 5 seconds. Which was really great because that was one small problem and a whole series of really hard problems we had to solve. And most notably, this was on a really crappy Windows laptop. So it just goes to show that if you resist the urge to throw technology at the problem and try to reframe the problem more simply, you can get some really valuable results. So the takeaway is, when faced with hard problems, try and approach it like a mathematician and might be better off. So that's all I had. Thanks.